And in this video we are going to talk about some basics of calculus. So as you know, in PD what we do is essentially we look for a function u, right? And so we deal with a function u which is generally defined on a domain D, right? And it is real valued function, so basically D to R. Now just for this part I am going to take D is a subset of R2. Okay, of course here I am doing it for R2, but the full theory whatever I am doing today, everything holds for any dimension. So n can be equals to 2, it can be 3, it can be 4, or any other dimension. Okay, so just for the basics and ease of understanding, we are just going to restrict ourselves to 2 dimensions, but you can do it for any dimension. Okay, so you have this function, let's say. So the first question we need to ask is, let's say I'm saying that this is continuous, right? Continuous, as you know, continuity is a point concept. So basically at some point, let's say x naught in D. Okay, so first thing first, we need to assume that D, this D, we will call this D as the domain of U. Okay, and it will be assumed throughout the course until unless I specify that whenever we whenever we are saying domain, what it means is a open and connected set. For now, let's just understand it this way: connected set. Okay, what is an open set? Open set, as you understand, is, let's say a D is open if if you take a point X in D, right? Then you can put a ball. There is a some epsilon small enough, a very small enough ball, and which will be contained totally in D. Okay, so does not matter for some epsilon positive. This is what we understand by a open set. This I think you guys already know, but still. So for example, as an example, think of it like B01. Yeah. So B01 is a ball. Okay. In, let's say, R2. Yeah. Because we are doing it in R2. So it's a ball in R2 with center 0 and radius 1. Okay. I can also write it like Bx naught, let's say R, and that will mean that the center of this ball, center is x naught and the radius is R. I hope this is clear. Okay, so that's what our notation is. Now see this ball. Okay, so if I want to put it properly in mathematical terms, what it means is essentially we are looking for x in R2. Okay, so such that the norm of x is going to be strictly less than 1. Okay, strictly less than 1. Okay, now we will also write it like some notation B01, the closure. This is called the closure of the open unit ball. This is the unit ball. Huh? This is called the open unit ball. So P01 bar, this is called the closure of the open unit ball. Okay, and this set will be defined as the set of all those elements in R2 such that norm of x, so everything in B01 and the boundary, so it will be less than equal 1. So you understand the boundary here is just mod x equals to 1, the unit ball. Okay, and of course del B01, whenever I am writing del B01, that will be set of all those x in R2 such that norm x equals to 1. Okay, and similarly for Bx naught R also you can define in a similar way, and essentially this is what, this is B01 bar minus B01. Yeah, so this is just basic notation which I am going to use throughout this course, and I am just clarifying that notations here. Yes, of course, any set may not be always B01, it can be Bx naught R, and in that case, you do it like this. So basically, let's say, let me put it as a question. So what is del B x naught R? Find it. Okay, and also find this thing. What is, let's say, B x naught R, the bar of it. What is it? Okay, so write down the mathematical part of it. Okay, fine. So that is basically an example of a domain. Connected means what? Connected means, very simply speaking, you take any 2 point here and you can join it along a path which always lies inside the domain D. So let's say D, I am saying it is connected. If you take any 2 points and you can join it in with a path, huh? The path which connect those 2 points. So there exists some path which will connect those 2 points, and the path should always be included in D. It will contain in D. Okay, right. So that's basically the domain. But generally speaking, in this course, mainly we will be defining. We will be talking about the domain D, which will look like this: AB, okay, cross CD. So this is the closed interval AB cross CD. So this is this set. Let's say this is AB, this is CD, C and D. So you have this set, okay, AB cross CD. Is it okay? Right. So essentially this set D here, so this is D bar, I will write it like this. So basically it will contain every point inside along with the boundary. Okay. So in this case, the domain, if you want to talk about the domain D, that will be open AB times open CD. Okay, so this is a open set. As you can understand, it is an open set, and of course it is connected and connected. It is very easy to see this, so please do this accordingly. It's okay, right? So now let's say, okay, so we have this ball and the domain. Okay, fine. So now we want to talk about functions, right? So let's say that given a u, okay, and let's say this is from this D, so let's call this as dr, okay, or maybe, I mean, if you want, we can just call it as an I is the rectangle. Doesn't really matter, I, R, whatever you want to call it. And similarly, let's call this as I bar. Okay, so u is defined from I to R. Let's say is a given function, is a given function. Okay, now I want to define the concept of continuity of u. Okay, so let's say we will say that, let's say x naught y naught is some point x naught y naught in I. Okay, given x naught y naught in I, u is continuous at x naught y naught. Again, you have to understand one thing. Yes, the whole point of this particular lecture is not to give you exact definitions, exact this theory. Okay, this is just I am assuming that you guys know all of this, and with that assumption I am just going through it. Okay, so u is continuous at the point x naught y naught if for any sequence, for any sequence xn yn converging to x naught y naught, u of xn yn must converge to u of x naught y naught, right? So that's your definition of continuity. Basically what I'm trying to say is this: let's say x naught y naught is some point. Okay, and the thing is this, and you do realize that there are like infinite number of ways we can approach this point, right? We can come towards this point. So essentially, see, we know that u will be given to us, right? So u at the point x naught y naught is given to us. We know what that is. What we are saying is, when is it continuous? We are saying u is continuous if it doesn't really matter which path you are taking, to go towards x naught y naught. Along that path, u of that, I mean, you take any point at that path close enough. Okay, so basically going towards x naught y naught, you take any point, that point, so u of that point, okay, the functional value of u at that point should also converge to u of x naught y naught. That's what it means. Okay, so for as an example, let's see. So let's say u of xy equals to a constant k. K can be 1, k can be 5, doesn't really matter. But so you can see it is trivially continuous. It is trivially continuous. Okay, why it is continuous? Can you guess? Okay, let's give you a simple answer. Let's say x n y n is any sequence which converges to x naught y naught, right? Okay, then you see what is u of x and y n. U of x and y n, that will be k for all n in n, right? Because u is always k. So u of x and y n doesn't really matter what x and y n's are. U of x and y n is going to be k, and that will of course converge to u of x naught y naught, right? So it is trivially true. Hence it is continuous. So that's one example. Now you can of course make a different lots of different examples. Let's say u of xy equals to some function phi of x times xi of y. Okay, where phi and xi are continuous. Okay, continuous where? Continuous in whatever domain x is varying and whatever domain y is varying. So basically in this case it is continuous in closed AB and closed CD respectively. Let's just understand that, respectively. Okay, right. So now the question is this function continuous? You understand? So I'm defining a new function u which is phi of x times psi of y, and phi is continuous in AB and psi is continuous in CD. Now we want to see whether the whole function is continuous or not. Okay, let's just understand. Let's look at the small proof of it. See, we are given, so x naught y naught is any point, right? So let's say I want to show that it's continuous at the point x naught y naught, where x naught y naught is the point. So let's say x naught y naught is some point. So start with this thing. So x naught y naught is some point in, for now let's just stick with open AB cross CD. Okay, let's do it for the open thing. Forget about the closed one. Don't worry about it, because generally continuity we define it for the open thing. So we define it for open. Okay, so we do it between AB and CD. Is it okay? Right. Now let's see. See, x naught y naught is in AB cross CD, right? We start with that point, and let an arbitrary sequence x and y n is an any arbitrary sequence that converges to x naught y naught. Is it okay? Now, if that happens, what does that mean? So what is the mathematical meaning of it? It means that the norm of xn minus x naught. Okay, so let me put it this way. It means that I'm just giving you the definition. Given epsilon greater than 0, there x will be delta greater than 0, such that basically u of, so that's what it means for a function to be continuous, right? X and y n should minus u of x naught y naught should be less than epsilon for all norm of x and y n minus x naught y naught less than delta. That's what continuity means, right? This is continuity in terms of epsilon and delta. Okay, now you see what's happening in our case. Essentially, let's say there is an arbitrary sequence x and y n which converts to x naught y naught. What does that mean? It means that x n y n minus x naught y naught, this is, see, less than delta, right? So essentially we have to show something like this. Let's start with this. We have to show this is less than epsilon for all x and y n minus x naught y naught less than delta. So what does that mean? It means that phi of x n psi of y n minus phi of x naught psi of x naught, this we have to make it less than epsilon. Okay, notice one thing. This is just a modulus. This is the norm, because u at some point that is going to be real number, so that is just a mod. But here x n y n and x naught y naught, these are vectors. So basically the difference of two vectors, you have to take the norm in R2. Okay, so I have to show this. So required to prove. This is for given epsilon, I have to do it. I mean, show that the difference is sufficiently small. Okay, if you have to do something like this, see, we can write it like this: x n phi of y n minus phi of x n. We will add and subtract this thing. See, y naught plus phi of x n psi of y naught minus phi of x naught psi of x naught. We can do this. Yeah. So essentially this means this. Okay. So now from the first thing, let's take phi of x n common. So we have psi of yn minus psi of y naught. Okay. Plus again, if you're taking common here, it becomes phi of xn minus phi of x naught. Okay. And then psi, sorry, when I made some mistakes, I think. Yes, this will be y naught. Okay, right. So it is psi of y naught. I hope this is clear. Now you use triangle inequality, it becomes phi of xn, sorry, phi of xn and mod of psi of yn minus psi of y naught plus phi of x naught minus phi of xn, sorry, xn minus phi of x naught and then mod of psi of y naught. Okay, now see the sequence converges. See, xn, we are given that xn yn minus x naught y naught is less than delta, right? Less than delta. So if that is the case, it means that xn minus x naught square plus yn minus y naught square is less than delta. Okay, so from there you can easily conclude that both xn minus x naught square is bound. So from here we can conclude that xn minus x naught, this square is less than delta, and yn minus y naught square should be less than delta, right? Very simple. So square of two numbers that is less than some delta, so each of them has to be less than delta. Okay, now if this is less than delta, so by continuity of phi you can make this very small, and again by continuity of phi you can make this very small. Okay, and what about this? This is a bounded number, right? See, xn converges to x naught. Basically, xn yn, if it converges to x naught y naught, it means xn converges to x naught. See, this is what xn converges to x naught. This gives you yn converges to y naught. See, if xn converges to x naught, it means that xn sequence is bounded. This will imply xn is bounded, right? Any convergent sequence is bounded, you already know. Again here, it means that yn is bounded. Okay, so if this is bounded, so what happens is phi of xn, this is a bounded term, and again this is also a bounded term, psi of y naught. Okay, fine. So you see, you can make this as small as possible. So basically you can make it less than epsilon. So this part I am not doing it, so please do check this yourself. Check it yourself. Okay, so make it less than epsilon. So of course epsilon will depend on delta. I hope you understood. This is a constant, this is a constant, and this term as xn as n tends to infinity, this converges to phi of x naught, so that is going to be a constant. This particular thing you can make as small as possible, this also you can make as small as possible. Okay, so please check it yourself. Now what is the beauty of this thing? The beauty of this thing is you can actually create a lot of different functions which are continuous in 2 dimensions. So let's say for example, if you take one function to be phi of x to be sine of x, okay, and psi of y to be, let's say, cosine of y. I'm just giving an example. Okay. Now you see your u of xy. So u of xy, which is sine of x and cosine of y, is continuous, right? So you understand that this is going to happen. Okay, so and you can change this function. So phi can be exponential, psi can be some other function which is continuous, and you can also write it like this. Okay, so all of this is true. Now I have some questions for you. So check that a times, so let's say u of xy, define u of xy as some constant a times phi of x, okay, plus b times psi of y, where a and b are constants, okay, and phi and psi are continuous functions, are continuous. Okay, show that u is continuous. It is very easy, right? So but you have to do it yourself. Please do it yourself, that phi is continuous for that. Okay, so with this we are going to end this video. Thank you.